Remember last time we were talking about DC test and we want to conclude that. And we are still on Hopkinson tests. But now we are talking about Hopkinson tests, excluding the fields. Remember last time we were talking about DC test and we want to conclude that. And we are still on Hopkinson tests. But now we are talking about Hopkinson tests, excluding the fields. So we have the motor and the generator. We have the current I1 getting in, generator giving us I what? I2. That is the field to the what? To the motor, and the field to generator. So that's the setup. When we say excluding the field, if you look at the previous drawing, you realize the field were connected at this junction, right? They were connected at this junction. But now, excluding the field are connected not to the armature. So that's what we call not excluding the what? Not including the field, or excluding the field. Let me call it I4. This is I4, I3. You find them in the example. Now, this is the point to note, that when you are excluding the field, in determination, of the constant loss, W what? C, right? Yeah? Do not include the field losses. Do not include the field what? Losses. Field losses. That's the secret that's here. Yeah? So if we begin with this in the theory, then we can begin by getting the motor, armature, copper loss. Remember armature is here, right? So what will be the armature current? I1 plus I what? I2. I think it's the current here. And then I2 proceeds, then you main with the I1. I1 is the supply, yeah? Right? So what are we saying here? The motor armature copper loss will be I1 plus I2 squared are what? Are right? Then we can also just conclude a generator. Generator, copper loss, given by what? I what? Huh? I2 squared R, because it's the only current coming from the generator, right? Therefore, total system loss at this point will be I1, I2 squared array plus I2 array. What is the system input? System input VI what? VI1, right? VI1 is the what was applied for this system. V times I1. The others are self-generated in the process. And therefore, what is the constant loss? Constant loss WC. Yes. Thank you. Squared. WC will be the input to the system minus the system loss, right? So we are saying this is V I1 minus I1 I2 squared array plus I2 squared array. WC, right? For each machine, for each will be WC divided by what? 2. And therefore, we can look at efficiency, the motor efficiency. So for us to start the motor efficiency, we need the motor what? Input. The motor input, in this case, that's another point that you need to note, is the power that gets to the field, right? Plus the power that gets to the armature. Right? And therefore, we say this is equal to armature input plus the field input. What is the armature input? Armature input, it's this one. I1 plus I2. But then it is VI1 plus, right? Because they are in parallel, plus VI what? I3. Dinaenda hapa. That's another challenge that is in this. When you say excluding, there are 2 points to note. One, during the point of getting WC, do not include the field. Right? Now, once we get that, then we can now just get the losses. What are the losses? Motor losses. First of all is armature copper loss, given by what? I1 I2 squared array. Field copper loss. At this point, field is now there. Yeah? We only exclude it at when you are getting W what? C. Field copper loss. V I what? 3. Constant loss. Constant loss. W C divided by 2. So the total losses will be given by I1, I2 squared array plus V I3 WC divided by 2. Therefore, efficiency in a motor is equal to P what? P in minus losses over P in a motor. So what are we talking about? What is the input? V I1 I2 plus V I3. I'm careful about my brackets. Minus losses, which include what? I1 I2 R V I3 plus WC divided by what? 2. All over V I1 I2 plus V I3. If you like to communicate in terms of 100, that will be the case. Then we can do the generator. Generator efficiency. In generator we talk of what? Generator output. The generator output will be given by V what? VI2. That's the rest we cannot determine, they are inside. It is VI2, it's the output. And then we can talk of losses. The first loss is armature copper loss, given by what? Which squared? I2 squared are what? Field copper loss, given by V and I of the field, which is I, for constant loss WC divided by total losses I2 RA VI4 WC divided by half. Therefore, efficiency in a motor is given by P what? P out over P out plus losses. So we are talking about VI2 all over VI2 plus I2 squared RA VI4 WC divided by half times 100. Efficiency as a motor, as a generator, sorry. Efficiency as a generator. Example. At 250 volts, 250 volts, DC machine, as a line current, of 50 amps, and motor current motor armature current of 400 amps. Not including the field currents, of 3.5 and 1.8. Not including the field currents, no, 6. My mind is another one. 5 amps and 6. Not including the field currents of 5 amps and 6 amps. The armature resistance for each machine is 0.015 ohms. Calculate the efficiency. The armature current is, for each machine, is 0.15 ohms. Calculate the efficiency for each machine. Calculate the efficiency for each machine. So you note the fact that not including the what? The field. And that means your diagram must appear like this, unlike what we did the previous time. So what is the voltage? The voltage here is 250. Line current 50. Armature motor current 400. Field current to the motor. 5. Remember we said the one with the higher field is the generator. So 4 here will be the 6. There's an equation we need to do. 400 is getting inside the motor. 50 is supplied by the mains, the supply. So how much was the generator giving out of 400? 350 is the current. Is the current I2. Did you hear me? Yeah? So that's the argument. We have to locate that current. Still, here is 400 coming, right? How much imepita? 3. So 50 is getting down, because it's the supply. So give that circuit. Give that circuit. Let's get on. We start with the motor. Copper loss. What will the motor copper loss? It is I squared, the I to the armature times the armature resistance. So what is the current getting in? 400, 0.15. Then we get a generator, because we don't have the field, copper loss. Still, we are talking about the I to the generator. Is a generator to the motor. So we are talking about 350 squared 0.15. Your calculator. Which one? This one? So what is the total loss? Total system loss. We added the 2, that is 2400 plus 18, 37.5. We get the total. Then we talk about system input, which is VI, which I 250 times 50, right? What is here? 42, 37, and 5. 250 times 50. Well, Eva. So we constant loss WC will be the system input minus the losses. So you are talking about 12,500 minus 42, 37.5. And therefore for each machine, WC divided by 2. How much? 8262.5 divided by 2. 4131.25. So that's the WC. That's the WC. So once you get a WC, then you can get the motor efficiency. Motor efficiency. We start with the motor input. Remember we said input is equal to the armature input plus field what? Field input. The armature input is V I1 plus I2. I1 plus I2 plus V I3. So we are talking about 250 times 400 plus 250 times 5 is the total input to the motor. The rest we have because we now have all the losses. Then 10 1250 flat. Then we get to losses. The first loss is armature copper loss. The IA squared RA. That is 400 squared. No, we have this. We are not repeating. It is 24, right? Field copper loss. Field, which is V I3 250 times 5. What did you get? And then we have the constant loss, WC divided by 2, which was 4131.25. So we can get the total loss, total motor losses. Add all this. Add all that. 17. 77. 81. 25. So efficiency is Pn minus loss over Pn. So we are talking about 101, 250 minus 77, 81, 25, all over 101, 250 times 100 as a what? As a motor. $92.3. As a generator efficiency, we generate output, which is VI, is 250 times 350, right? And then we have the losses. We have the armature, copper loss, the IA squared R. This is same, 350 squared, 0. We add this. Yeah. 18? 1837.5. Field copper loss, that is VI of the field, 250 times 6. Constant loss, WC divided by 2, 41, 31.25. What is this? 150, 1500. Total loss, add all this. Total loss, $74.75. And therefore, efficiency is P out plus loss. What was 250 times 350? 87. So we are talking about 87,500 all over 87,500 plus 74.68 times 100. 92? Very minor different. So that's about excluding. So the other one that I also need to mention is about auxiliary. The auxiliary circuit is the same, but now you include the field. You include the field losses at this point. So that's the example that we do. Next. The auxiliary fields. So I want to use it I want to use example, then we execute it. Here point to note NB. Include the field losses when determining the constant loss W what? C. So when they talk of auxiliary, the circuit will be like this, but include the field what? Losses. It look like this. Just like in the case of excluding. But now in the determination of, remember in the previous excluding, we only look at the armature losses only, and then we got the W what? C. But in this we say include everything when you are getting W what? C. So let's get this example. In Hopkinson test, of a pair of in Hopkinson test, in a pair of 500 volts, 100 kilowatts, shunt generator, 100 kilowatt shunt generator. The following data were obtained. The following data were obtained. The auxiliary supply is 500 volts, 30 amps. Generator output current output current 200 amps. Field currents is 3.5 and 1.8. Armature resistance is 0.075. brush drop per each machine is 2 volts. Brush drop for each machine is 2 volts. Calculate the efficiency. Calculate the efficiency of the machine acting as a generator. Calculate the efficiency of the machine acting as a generator. So that's the drawing. Let's just substitute the values first. Here is 500, right? The auxiliary current getting it is what? 30. Generator current is 200. So that means how much is getting down here? Huh? How much is getting inside here? 230. The field here is how much? 1.8. The field here is how much? 3.5. Huh? And therefore, 230 is coming here. 200 is getting to the system of the generator, and 30 is going back to the main circuit. That is the circuit. The concept, if you look at the concept, it's just flowing. Huh? Yeah? Concept is just a normal one that is flowing. And that's why I'm telling you, don't be surprised by the value of the expression. Look at the concepts. In any engineering derivation, they don't get more than 4 concepts. Huh? Let's look at this. And therefore, we start with the motor. Let me begin with the way we start. Motor input will be what? The armature input, right? Yeah? The armature input plus the field. So what do you have? 230. Let me start with the voltage. 500 times 230 plus 500 times 1 point what? Right? That is input to the what? To the field. So we have that's the total input to the motor. And then we can look at the losses. Losses, we are saying we start with the armature. Armature copper loss given by I squared RA, which is what? 230 squared, 0.075. That is the loss in the armature. Point to note, there was a brush drop of 2 volts per each machine. No, each machine, not per brush. Huh? Each, yeah, not per brush, and therefore we are saying the brush drop loss is given by the armature current times the volt drop, which is 2 volt. So what are we saying? 230 times 2. 230 times 2. I'm waiting for your values. Then we get the field copper loss given by V times the current of the field, 500. Current of the field is 1.8. So what do you get here? The first case? 11? 59? Evo? 11:59:00. Are you up here? Am I here? Yes, because I suspect him. That could scare me. 11:59:100. The copper loss? 50:25.5, followed by 460. Then? Which one? 0.075.
3967.5.
Which one?
That must be that.
So it's not 50. You're saying 39?
67.7.
0.7.
3967.5.
Right. Next.
900.
Total loss. Add this.
Total loss is 53.27.5.
53?
27.5.
So we're done with the motor. So generator. We talk of the generator output. VI 500 times 200. 100,000? 100,000? Please confirm. Losses. Amateur copper loss. I squared R. Array. 200 squared times 0.075. Brush drop loss. 2 volts times the armature. 2 volts times 200. I guess this is 400. Field copper loss. VI of the field 500 times 3.5. Calculator, what's the calculator saying here? Yeah? 3,000. Point? Flat? Okay. 500 times 3.5. Field copper loss? 1750. Total losses? 81? 51? 50. Point? Total field loss, total system loss. That is the loss for the motor plus what? Generator loss. So we are talking about 53 27.5 plus 5150 as the total system loss. System input. What was the input to the system? Look at the diagram. What is the system input? The VI is 500 times what? Times 30, which is 15,000. Add the losses. Add loss.
You get 10,477.5.
10,400.
77.5.
77.5. So what is the constant loss? Constant loss WC is the system loss minus system what? Oh, system input minus system loss. So 15,000 minus 10,477.5. For each machine, what do you get here? 40? 22.5 divided by 2. 22? 61.25. So that is the WC. What is the question? Determine as a generator. So in that case they are specific, right? So generator efficiency. So in generator we talk of generator output, VI, which is 100. Losses, we have the armature copper loss, which is 3,000. Brass loss, $400. Fields, copper loss, 17, 1750. Constant loss, WC divided by half, 2261.25. Total loss, add all this, add to, we had a total loss, I don't know, to this add 2261.25. What do you get? 6411.25. Therefore, efficiency is P out plus what? Loss. That is 100,000 over 100,000 plus. Let me pause so that we can vote. of any contrary opinion. Let another person confirm. Huh?
74,
Huh?
11.
So we vote. 70?
74, 11.25.
74, 11.25 times 100. That is all about, that's all that I could do around that DC. If you run through those things, you are safe. So that we prepare for next, I'll be introducing induction motor. Induction motor. Have you seen induction motors? Huh? Where?